Yes, or before proving this theorem or reading the statement, I give you an example to understand what is the statement. I have two numbers 4 and 6. The divisors of 4, 1 is divisors of 4, 2, 4. These three are divisors of 4. Now divisors of 6, I am writing divisor 1 multiply 6 is 6. 2 multiply 3 is 6. 2 is also divisor. 3 is also divisors of 6 and 6 is also divisor. 6 ones are 6. Here 1 and 2 are common divisors. ठीक है, CD common divisors are 1 and 2. What is GCD? Greatest common divisor is 2. What is the greatest common divisor? Which is the greatest number which is divisor is 2. So here we can write 4 and 6 have common divisor 2. Actually our proof is this: if I divide this number with greatest common divisor and this number with greatest common divisor, then the resulting numbers are relative prime. They have no common divisor greater than 1. This is our theorem. Now this is a specific example with numbers. I consider now general case. If I have A and B, two numbers having GCD 1, then just like that. So the GCD if 2, then 2 divides 4 and 2 divides 6. Okay, then D divides A and D divides B. Okay, one thing. Then we have to prove that if I divide this number with GCD A over D and B over D, then its GCD must be 1. There is no common divisor greater than 1 of these two numbers, just like that. This is our theorem. Now I read the statements. Statement: if A and B belongs to set of integers Z where A and B are both non-zero, okay, and A, B, GCD is D, then if I divide A with D and B with also D, then their GCD must be 1 or they are relative prime. When numbers are called relative prime, when their GCD is 1, they have no divisor greater than 1, no common divisor greater than 1, they have greatest common divisor 1, then they are called relative prime. If A divides here D divides A, if D divides A, just like that, if 2 divides 4, then 4 can be written into multiple of something. And also if 6 2 divides 6, if 2 divides 6, then 6 can be written in the form of 2 multiply 3. We can write it this. If you see that here we take at the place of 4A and here we take B and this is the D, therefore D divides A and D divides B. We prove this, we want to prove this. Okay, if D divides A and D divides B, okay, this is D, okay, this is A, this is D, this is B, then what we can write this: A is equal to D, I suppose this number in generalized form a1, and this is b, and this is d, then I suppose this number, I give the name to this number is b1, then there exist a1 and b1, two numbers. So if d divides a, d divides b, then a can be written as a1d and b can be written as b1d. Okay, therefore a must be equal to a1 is equal to, divide this d goes in denominator, okay, as you know that, and b1 is equal to this d became denominator. Okay, now what we prove this, what is this is a1, what is this is b1. It's mean if we prove this, we want to prove a1 and b1 is relative prime, have greatest common divisor 1. This is our destiny. Okay, now I write this thing which I explain you here, as it is given that a and b have GCDD, then d divides a, d divides b, I write here. Then if this is multiple and this is divisor, so multiple can be written as these two factors. If this is multiple, this is divisor, then multiple can be written in the form of two factors. So a1 d become the denominator, b1 is equal to d become the denominator here. So we want to prove that a1 over d and b1 are relative prime. This is, so I suppose I take a common divisor. I said that I suppose that this is not true. Okay, this is not true. So if it is not true, both have a common divisor c. So c divides a1, c divides b1. If it divides this is divisor, this is multiple, so multiple can be written in the form of two factors, any number here which we multiply with this, so become a1. For example, c is 4 and a1 is 8, for example, so 8 can be written in 4 multiply 2. This I give this number name d1. Okay, just like that b1 can be written c into d2. You know that in I put this value, put a1 and b1 value in equation 1 and 2. Okay, 1 and 2. So a is equal to a1 is c d1. Okay, and at the place of a1 I replace a1 with c d1 in this equation d, and therefore b becomes, I replace this b1 with the value of b1 c1d. Okay, what is the value of b1? cd2, and then this d I write here, this d. Okay, now can I write cd into d1? Okay, and here I write d2 at the n place. Here a and b is equal to cd d2. Can I write 3 multiply 5 multiply 6 as 3 multiply 6 multiply 5? There is no change in answer, so I just change the places of multiplication. Okay, here you see that this number can be written in the form of 3 factors, and this also can be written in the form of three factors. If I multiply this number, so these all are divisors of this, because these are factors and this is multiple. So CD divides A and CD divides B. Okay, CD divides A and CD divides B. If CD divides A and B, so CD is common divisor. Divisor of A and B. If CD is common divisor, then CD must divide the greatest common divisor of A and B. CD must divide CD. How can it is possible that 3 divides 3 and then I multiply with some number and then this expression is true? Okay, D is equal to D, and if I multiply with some number and then it divides the D, how it is possible? Only in one case, when this C is 1 plus minus 1. So as C is greater than 0, as we see that C is greater than 0, so we take, which implies C must be equal to 1. If C is equal to 1, what we decided here, that there is no other divisor of A1 and B1 other than 1. We take a divisor, that divisor become equal to 1. So our theorem is proved, because A1 has value A over D and B1 has value B over D. So it is proved that there is no common divisor greater than 1. This is our theorem